Hello everybody, welcome back to another Gregorious Math video. We're back in business. Yeah. And we're going to be doing higher homotopy groups. And so this is a generalization of pi 1 of x, which is the fundamental group. And pi 0, I haven't actually introduced it in the topology series, but it's the set of path components of x. And so you have pi 0, you have pi 1. Actually, this is not a group, but you have pi 0, you have pi 1. So now we're going to look at pi n. Alright, and we do get some interesting properties. It does get a bit trickier. It's a lot trickier to compute pi n in general than just specific cases, of course. And the homotopy theory, I mean topology 2.1 to 2.9 this video is just basic homotopy theory, but homotopy theory can get like really complicated when with infinity categories and all that stuff as well. So this is just the basics. So even if this seems somewhat daunting, remember that this is just the basics. So homotopy theory can get pretty scary. Hopefully that's encouraging you to look into it a bit more rather than discouraging you. But yeah. So we're going to be looking at pi n and some basic properties and a few definitions which we might use in next videos. So pi n of x actually has a simple definition. So there's two different ways to define it, but I'll use the more simple version, which is just the set of homotopy classes it's the set of homotopy classes of base maps. So base maps means it takes base point to base point from the n sphere to x. And this does agree with our previous definitions. For example, for pi 0, remember it takes it's based maps. So it takes one of the points in the 0 sphere to x, and then the other point, to the base point in x, and then the other point to x. So it's the set of path components, right? And okay, let's see. Well, an observation which turns out to be useful, very useful actually, combining this fact right here with the idea that you apply the functor pi 0 to fiber sequences of the loop space, gives you some nice long exact sequences. And so we're going to have that pi n of x is equal to pi n minus 1 of the loop space of x is equal to oh my goodness, is equal to pi 0 of the nth loop space of x. Okay? And so using this fact, so say for example we have a sequence of loop spaces, blah blah blah, then we just apply the functor pi 0 and then we get an exact sequence of homotopy groups, which is a common theme, as you'll see. And okay, so this is a quite elementary property, and again, useful. But let's see what else we can conclude. So, for example, if we have a base point star in A, a subset of x, then we define the space of paths, we denote by P of x, and then you have star, the base point, A, is the space of paths in that's in x, in x, that start at the base point and end in A, the subset of x. Okay? Alright, so now, using this, we can actually generalize the generalization. So, we can have homotopy groups of pairs of spaces. We say that pi n of x at a equals pi n of x, a, and then the base point. And then this is equal to the n minus 1th homotopy group of the space of paths in x at the start of the base point and end in a. Alright, and now we're ready to look at some fiber long exact sequences associated with these. And to do this, we'll look at the fiber sequence of loop spaces, basically. So let's define fi by p of x, and then we have the base point a. Then we have the fiber sequence. So we're gonna have blah blah blah, and then we're gonna have coming in. We're gonna have the second loop space of a, and then we're gonna have the second loop space of x, and then we're gonna have the loop space of fi up until. Sorry, actually, I'll do this because I'm only at the second one, really. I'm not that lazy. To the loop space of a, to the loop space of x, to the just fi, to the loop space. Sorry, not the loop space. To the to a to x. All right. So this sequence on its own is just a fiber sequence, right? But it gets more interesting. So we obtain, alright, by applying the functor pi 0, alright, we obtain by applying the functor pi 0 the long exact sequence so we have the long exact sequence. So we remember that pi n of x is equal to pi 0 of the nth loop space of x, or in other words, for example, if we apply pi 0 to this, we're going to get pi 2 of a, right? So in the end, we're going to have coming in, we're going to have pi n of a, and then this is going to go to pi n of x, and then what's it going to go to here? Well, this is the loop space of this. And now let me add one more line here. This is equal to pi 0 of, well, remember this is n minus 1, not n. So we're going to get the n minus 1th loop space of this. Right, because we have n minus 1, so we're going to have pi 0 of n minus 1. And that's what this is right here. So we're going down to the n minus 1th. So this is just 2 minus 1, right? And so we're going to have the n minus 1th loop space of this. And so when we apply pi 0 to it, if we go back around here, we're going to get this. Alright? So then we're going to go to pi n of x, a, and then we're going to go down to pi n minus 1 of a. So on up until pi, sorry, and this goes via del, and I'll define del in a second, and this goes all the way up until pi 0 of a, and then we're going to have pi 0 of x. Alright? So we have this, and, well, what's del? Okay, we just have this random map in the middle there. Well, first we're going to sort of redefine pi n of x a. Right? So, let's see. First we have to define a more specific space. So J n, this is the common notation for it, I believe, is defined as the boundary of I n minus 1 with the convention that the boundary of I0 is the empty set, we have the boundary of I n minus 1 cross I union I n minus 1 cross 0. Alright, so this is what J is. And now we have pi n of x a star is equal to, and now we're going to have homotopy classes of maps between triples, and I'll explain the notation in a minute. Let me just write it out. So we're going to have in, I'm going to have the boundary of in, jn, and then we're going to have x a star. Of course, they have to come in somewhere, right? And this notation just means that in is a map from in to x, and then it sends the boundary to a and jn to the base point. Okay, so every map sends jn to the base point, boundary to a, and and it's a map from in to x, as you might expect. And alright, so now that we have this, we obtain del the function del, which takes from pi n of x a to pi n minus 1 of a, by restricting maps from this triple to that triple, from in. Actually, we'll start writing up here so that I have space to write this all out. Restricting maps. Alright, let's see if I can do this. From in, boundary of in, jn, to x a star, nice, to maps from the boundary of from in minus 1 cross 1, and then they have the boundary of in minus 1 cross 1, and then this goes via to a star. Okay? And similarly, this long exact sequence here, so pi n a to pi n x, and pi n x to pi n of x a are both, the maps between them are both induced by inclusions from x at the base point to a at the base point, and x, and then the triple x star star to a x star, basically. So, alright. Now that we have some of that out of the way, I'll stop to provide a few simple and elementary properties which one should know. Well, I'll state without proof. So, the first one is that pi n of x cross y is isomorphic to, it's homeomorphic to, homeomorphic, is isomorphic to pi n of x cross pi n of y. Alright, so this not only works for fundamental group, but for n higher homotopy groups. Now, pi n of Sn is always going to be isomorphic to the integers. That's quite a substantial result. As you'll see that computations of higher homotopy groups of spheres does get very messy and very complicated easily. There are massive tables which you'll find, which are really interesting to look at, but they do get super messy. Beautiful chaos. But pi n of the n sphere is simply just the integers every time. And that takes a bit of work to prove, which I won't go into right now. Pi n of Si is just going to give you 0 if I is bigger than n. Okay? And, well, a lot of these are to do with the sphere, but these are some elementary properties that one should know, especially this one. So when computing like homotopy groups of toruses, tori, I'm not sure what the plural is, you can just consider homotopy groups of spheres, for example. Alright, so that's just a few basic calculations. But alright, let's see, what else is there? Okay, so I'm just going to introduce some language, which might be useful in later videos, because of course, this channel is mainly about shorter, intros to topics you might find 1-hour lectures on, so this is not as detailed, but it will provide you with probably all the information you'll need in order to watch the rest of the topology series. So the last thing I need to do is define an n equivalence, or a weak equivalence. So, we say that E, for a map from Y to Z, and is an n equivalence if given some y and y, and also pi n of x at some x is defined as per usual. And I'm not going to go into the discussion of the change of base point in this video, unfortunately. Given the y and y, we have it that E star from pi q of y at y to pi q to z at e of y is an injection for q less than n, and a surjection for q less than or equal to n. And it's a weak equivalence. Okay, I'm actually not sure about the name. I think we could have named it a bit better, because it seems like quite a strong condition. But it's a weak equivalence if it's an n equivalence for all n. And well, yeah, that's it for today's video. Hopefully you found this informative. You at least got the basics and a few ideas from homotopy theory, such as, you know, applying the functor to fiber sequences to obtain long exact sequences. And yeah, I'm sure you can do more digging after. I hope you found this somewhat illuminating. But again, it's not like as detailed as, you know, of course, because it's shorter. It's not going to be as detailed as the hour-long lectures. You might not have time to watch, but hopefully this has at least whetted your appetite for some more homotopy theory. Unfortunately, I won't be doing more homotopy theory in this series for at least a while, because I'm going to take a little detour to do CW cell complexes, and then I'm going to do various different homology theories in algebraic topology, then the same thing with cohomology, and then we'll see where we end up with. I might do some special, more advanced cohomology theories, might do some stuff about characteristic classes. You know, there's a lot of different ways I could go, and I'm planning to cover them all eventually to get like some massive 70 video topology series where I cover tons of advanced algebraic topology, all condensed into 20, 30, maybe even 40, although I don't think I'll come to that minute-long videos. But yeah, for now, hopefully this has whetted your appetite for some more homotopy theory, and hopefully you enjoy your mathematics. Goodbye.